Hello, I am Wouter Janssen, a researcher at Cosys-Lab, a research group at the University of Antwerp in Belgium. Today I would like to talk to you about and show you our real-time 3D sonar sensor. Sonar is a sensing modality that does not require a lengthy introduction. Many species of bats have shown excellent navigation behavior as well as being able to classify objects such as their prey using their biosonar. It is there that our research group found their initial inspiration to develop advanced sonar sensors. Not the simple type to use as a parking sensor on a vehicle, but advanced 3D imaging sonar sensors capable of much more. For many years, these sensors have been in development at our lab, and today we would like to show you our eRTIS sensor, an embedded, real-time 3D imaging sonar capable of high spatial resolution imaging. Our sensor can do this by using our custom microphone array as seen on the images. A bat has a single emitter in its mouth and 2 ears as input channels. We use a single emitter as well as a sparse array of 32 microphones. This allows us to capture all the reflected echoes in the entire frontal hemisphere of the sensor. Using our embedded platform, we can process the recorded ultrasonic signals of these microphones and create 3D images 10 times per second in real time. In today's presentation, we will show the 3D images that our eRTIS sensor is capable of making, as well as a high-end 3D LiDAR sensor. In this demonstration, we will be using the Auster OS1 LiDAR. A LiDAR sensor uses laser light and measures the reflected light using image sensors. This version presented today has 64 channels and has a horizontal resolution of 2048. Its vertical field of view is rather narrow at just 33.2 degrees, however, it does capture the entire surrounding area around the sensor horizontally. It has a long range of up to 120 meters and creates a very high-resolution 3D image of the environment. In this demonstration, the 3D point cloud images will have over 600,000 points per second on display. Comparing the numbers then to our sonar sensor, we use 32 channels. Our vertical field of view is much larger at 180 degrees, however, we are limited to the frontal hemisphere of the sensor and cannot look behind it. The range is less compared to high-end LiDAR at just 30 meters, and the point cloud you'll be seeing has a lower density. However, comparing these sensors just by their specification numbers doesn't do them justice or doesn't show what this comparison is really for. While LiDAR on paper will produce much more high-resolution point clouds, it does so when the conditions for it are great. Once conditions deteriorate, these sensing modalities based on light, such as LiDAR or common cameras, will cause their sensing capabilities to drop significantly, where autonomous systems might not be able to use their sensor data for tasks such as autonomous navigation. The medium of light can be distorted by dust, dirt, fog, rain, sunlight being varied with the day and night cycle and the seasons, as well as LiDAR not being able to sense glass objects very well as the infrared laser light will go through it. High reflective objects can also disturb the capture of the LiDAR sensors. Sonar, on the other hand, uses a different medium, the acoustic medium. This is not disturbed by these conditions and can continue to operate normally under them. However, it as well has its limitations. Sonar uses sound, so the speed of sound is a limiting factor. Therefore, using sonar on high-speed vehicles on the highway is not a good idea. So we are not comparing the sensor specifications in this demonstration, but it is really about explaining the different application fields of these sensors, and no matter how good these sensors are, sensor fusion will be the key for most applications in the future, where multiple sensors using different modalities can work together to provide enough sensory input for performing autonomous tasks no matter the conditions of those mediums. And so, sonar being very capable in rough conditions such as dust, fog, or rain means we target heavy industry, agriculture, and industrial logistics, not autonomous road vehicles. With that said, I would like to present our footage of the 3D sonar sensor together with the LiDAR sensor. Here, both sensors are shown in their demonstration configuration. After the demonstration, I will discuss a few more technical aspects of our sensor and some closing remarks. The point cloud you can see in gray is that of the LiDAR, and the colored point cloud is that of the sonar, where the color is varied with the range. As you can see, the point cloud of the LiDAR is clearly larger and holds more detail to allow for the human eye to distinguish objects. The sonar sensor point cloud, however, continues to detect all important objects such as the person, the chair, and the walls. As also can be seen here, the LiDAR does not detect the windows. And once again, we want to emphasize that both sensors target different applications for different conditions of the environment. To achieve these 3D images, we perform signal processing on the audio signals captured by our microphone array. The digital ultrasonic audio signals are first demodulated, after which we find the original pulse the emitter sent out with the matched filter. We can now pre-calculate the delays determined by the speed of sound, the position of the microphones in the sparse array, and the source of the sound. We essentially steer the microphone array in the directions of interest. This is called beamforming, for which we use a delay and sum beamformer in the time domain. To make the images cleaner, we use an additional step such as an envelope detector. A last note on the beamforming. By choosing the directions of interest, we can scale the spatial resolution and choose the field of view of the sensor. If we, for example, build an application that only requires information on the horizontal plane, we can only perform beamforming in these directions as shown here by the blue arrows. On the other hand, if we want to fill 3D's frontal hemisphere, we can choose many more directions as used here with the red arrows. We achieve our real-time performance with our own signal processing software, which uses embedded GPU processors. We hope you enjoyed the demonstration. We continue to develop our sonar technology as well as building applications using them, such as, for example, autonomous robots. On the right, you can also see a new iteration of our sensor, which comes in a much smaller package. If you have any questions or want to see our sensor technology for yourself, don't hesitate to contact us.